All right, so today's topic is acids and bases. So our goal today is determine, given a bunch of compounds that are acidic or basic, which one of those will be the strongest acid or the strongest base. All right, so let's take a small step back to general chemistry. Hopefully you remember this equation, which describes how acid-base reactions generally work. So you have some sort of acid, it donates this proton to water, and you get H3O plus and this conjugate base over here. And we have an equilibrium constant, which we call Ka, which is a ratio of these elements over here. And you know, or you should know, that if your Ka is large, then it means the extent of reaction goes very far in the forward direction, which means almost all of this is converted to this. So what that means is that your acid dissociation is incredibly high. Now you should also remember what this P means. If you take the pKa of something, you're taking the negative log of the Ka. So if you have a large Ka, what that means is that you have a low pKa. So again, a large Ka gives you a low pKa. So if your pKa is incredibly small, you're looking at a strong acid. So again, why do we care about this? Well, what this tells us is that in general, if your acid is strong, if the Ka is large, if the pKa is low, it means your conjugate base is stable in comparison to the acid. Remember, whenever you use the word stable, really talking about reactivity. It means that this A minus over here, this conjugate base species, is stable in relation to HA. So HA will be highly reactive, and most of it will be converted to the conjugate base, A minus. So the general relationship we have here is that the more stable your conjugate base is, the more stable A minus is, the more strong your corresponding acid is. The principle you look at in general chemistry is pretty much the stronger the acid you have, the weaker the conjugate base. So for instance, if you have hydrochloric acid, that's a strong acid, so that goes to H3O plus and chloride anions. And chloride anions are an incredibly weak base because Cl minus is pretty stable. So when we talk about stability, we're really talking about that conjugate base's ability to stabilize a negative charge when it has it. Okay, so today's objective, if we're trying to rank the acidity or basicity of the compound, we're really looking at the conjugate base's ability to hold a negative charge. So let's dive right in. So there's a series of rules that were developed for how to tell how stable a conjugate base is going to be. And these rules are outlined very well in David Klein's Organic Chemistry as a Second Language, where I'll be pulling most of this information. If it's your first semester taking organic chemistry, I highly recommend getting this book. It is incredibly useful and incredibly easy to read. All right, so the first factor that we care about when we're looking comparing two compounds is the atom that bears the negative charge. So what do we mean by that? Okay, so first of all, let's look at a periodic table, particularly the portion of the periodic table that corresponds to where most of our organic compounds are going to be. If you remember your periodic trends, you remember from the left to right in a row, the electronegativity increases, where fluorine is the most electronegative. And for instance, oxygen is more electronegative than nitrogen. The more electronegative an atom is, the better its ability to stabilize a negative charge or to bear a negative charge. Similarly, as you go down along a column, the size of the atom increases. The larger your atom is, the better it could bear a negative charge. And the reason is because instability comes from when you have a large amount of charge packed into a small amount of area. If you remember from general chemistry, things like hydrobromic acid and hydrochloric acid are considered strong, but hydrofluoric acid is considered weak, because while fluorine is incredibly electronegative, it's also incredibly small. And if you're packing that much negative charge into that small space, that isn't stable. So you're really looking at a balance between how electronegative you can get and how large you can get. The principle you'll see in a lot of these is delocalization of charge is highly preferred. So an example of this would be comparing these two species. So really, which one of these is more stable? Well, if you look at the periodic table, you'll see that oxygen is to the right of nitrogen, so it's more electronegative. It's going to more easily stabilize this negative charge. Similarly, if we look down the column, we can see that we're comparing these two species, one with oxygen and sulfur. The sulfur will be more stable because sulfur is larger than oxygen, and it will more easily be able to maintain that negative charge. Okay, so the next factor that matters is one that matters across the board in a lot of places in organic chemistry, and you've probably guessed it, it is resonance. So the reason why resonance is so good is again, it's this idea of delocalization. If you haven't heard of delocalization in lecture, delocalization, it essentially means spreading out charge. When your electrons can move from one atom to the next through a delocalized electron cloud, that's very good for charge stabilization. And that's why resonance is so good at making things more stable. And the example will be this. So if you look at just a regular alcohol, like ethanol, and you deprotonated this, if you got rid of this hydrogen, you'd have a negative charge here. And the only place that negative charge can go is on that oxygen atom. It's the only charge bearer. However, if you look at this kind of system here, where you have an aromatic ring, a benzene ring, if you deprotonate here and there's now a negative charge on the oxygen, it could be spread out into this ring. So really you have 6 or more atoms bearing this negative charge now, which is a lot better than having the charge stuck on just one. Similarly, if we look at this carboxylic acid group, you'll also see that the pKa is much lower than these two because you have charge delocalization, you have resonance. If we deprotonated here and we made this negative, we'd have the electron pair being able to go between these 3 atoms. And if you have resonance with electronegative atoms, such as oxygen, that's very, very, very good. You can see that just having resonance between these 3 atoms with the oxygen is much better than having resonance across 6 atoms with the carbons. So resonance structures with electronegative atoms are preferred over electropositive atoms. All of this will be more clear when we start doing some examples, but let's look at our third factor. This is the one that people usually have the biggest problem with. This is induction. So when we're talking about induction, again, you should look at it and keep it in the context of charge delocalization, that is spreading out charge. So if you look at these 3 species here, what we're talking about when we're talking about induction is we have charge delocalized over here, but how do the groups over here affect that? Well, hopefully in lecture you've discussed that alkyl groups are electron donating through a phenomenon known as hyperconjugation. So if you have 3 methyl groups over here and you're trying to spread out this charge, well, you have electron donation happening from here into here. So you're actually putting more charge into an area that's already charged. That's pretty bad. Over here, though, it's more stable because you don't have that electron donation effect. There's only hydrogens over here, and you're not having the pushing of those electron donating groups. On the other hand, if you have something like a electronegative atom over here, like a halide, these are what are known as electron withdrawing groups. So remember, your highly charged center is over here. This is where all your charge is. And if you have these groups pulling charge away from that very charge dense center, then you're spreading the charge out among more atoms. So that's, again, more charge delocalization. The more spreading out this charge you have, the easier it is for the compound to bear it and be more stable. The last factor is a little bit subtle, but it also matters a lot. It is the orbital that is bearing the electrons. So The principle there is if we look at these three different compounds with different hybrid orbitals, here we have an sp3, an sp2, and an sp, each bearing this negative charge, we expect the sp orbital to be the most stable. The reason for this is all of these orbitals have different amounts of p character. And if you remember your p orbital shape, which looks like a figure 8, you have basically, if you had the nucleus here, your p orbital would spread out above and below. That's getting farther away from the nucleus. So if you have more s character, those electrons are allowed closer to the nucleus, which it has that positive charge that could balance out that negative charge. So remember, sp3 has 75% p character and 25% s character. So those are large orbitals with a lot of electron density found away from the nucleus. That's not so stable. But over here with sp, that's 50% p character, 50% s character. It allows those electrons to get much, much closer to the nucleus, which stabilizes this negative charge. So again, just to review, the reason we care is we're trying to rank the acidity or basicity of compounds, and we figured out that the more stable our conjugate base, the stronger the acid that corresponds to it will be. And the reason is because of this, I guess, charge stability phenomenon here, where if you have that negative charge, the compound that is most easily able to bear that negative charge is going to have the strongest conjugate acid. Okay, so to summarize, if you're taking notes, I would recommend this to be what you should copy down. So the way that we're going to be able to solve problems is first we're going to look at the compounds that we're given, and if they're acids, we're going to convert those compounds to whatever their conjugate bases are. So we're just going to deprotonate or remove one of the hydrogens. Second thing we're going to do is once we have those conjugate bases, we're going to look at each of these factors. We're going to make a table, and then after that we should be able to decide which one of these compounds will be the most stable based on these factors. Once we've done that, we could rank them and then rearrange them based on whatever the question is asking. And it'll make more sense once we start solving those problems. So let's do that. So the first problem we have is this. We're given a bunch of compounds, and we are asked to list them in the order of decreasing pKa. Okay, so in our algorithm, the first thing I recommend you do is you change each of these to a line wedge representation. So each of those species looks like this. You should be familiar with how to do this by now. It makes it a lot easier to see how things happen. The next thing you want to do is that first thing we said in our algorithm, it is to convert each of these acids to their conjugate base. So, well, the way we do that is we find the most acidic hydrogen in each of those species, which is each of these, and we remove them, and now we have a lone pair with a negative charge there. Okay, now we start looking at our factors, and we start filling in what we have. So our 4 criteria were the atom, whether it had resonance stabilization, how the inductive effects affect things, and the orbital. So for each of these, it should be rather obvious which atom is bearing the negative charge. So it is whichever one has that formal charge, the minus sign next to it. For resonance here, you don't have any pi electrons, so there's no way that any of these species is going to be able to undergo resonance. So that's going to be no's across the board. Okay, what about inductive effects? Well, there's nothing going on here on the left. There's pretty much nothing around here to balance out or do anything on that amino group. There's nothing going on here, but here we have a fluorine, and here we have those methyl groups. So when we're talking about induction, why do we accept this as good induction and this as bad induction in regards to stability? Well, here we have an electronegative element pulling electron density away from this center, so we have a little bit of charge delocalization. Here we have, if you remember, each of these methyl groups is electron donating, so they're going to be pushing electron density back over here to this charge center, which isn't favorable for stabilization. The last thing to look at is the orbitals involved. Hopefully you know how to determine the hybridization. There's a separate video for that, you can check that out. But each of these is going to be sp3. Okay, at this point, we have enough information to be able to decide what the most stable compound is going to be. And the first thing to do is, if you don't remember what the periodic table looks like in that top right, you should get that. So remember, the first thing we care about is the electronegativity and the size. So here you can see that oxygen is better than nitrogen, so you know off the bat that these three are probably better than nitrogen. So nitrogen is going to be our worst. Sulfur beats oxygen. It's larger, so it's more easily able to maintain that negative charge, so it's going to be the best. So I'm going to put an A here and an E here, where A is the most stable and E is the least stable. Okay, now we go to each of these. They don't have resonance and their orbitals are the same, so the only thing we can compare is their inductive effects. Well, here we have good induction through the form of electron withdrawal, so this is our second most stable. Here we have nothing and here we have bad. So having nothing is better than having bad. So here is our stability ranking in terms of the conjugate bases. So again, we're going from most stable to least stable in A to E. Okay, the question asked us to list them in terms of decreasing pKa. So decreasing pKa, if you remember, a large Ka, it gives you a small pKa, so we're going from worst acid to best acid if we're in decreasing pKa. What that corresponds to is low base stability to high base stability. And that tells us how we could rearrange this order to get what we actually want. If we're going from low stability to high stability, then we're going to go reverse of our order. So we're going to go E, D, C, B, A. And if you do that, you realize that the order is going to be 2, 5, 1, 4, 3. And that's the answer to this problem. Okay. This time I'm going to let you attempt one. Now that you know the basic procedure, and how about you give this one a try? And I'll stay silent for 10 seconds, and you should give it a try on your own. Okay, I'm going to assume that you tried it. So the first thing I would do once again is convert all these acids to their conjugate bases. So that looks like this. Then once again, we're going to go through each of our criteria from top to bottom. So the first is, what atom bears the negative charge? Well, it's simple in this one, each of them is going to be oxygen. Well, I should point out what we have here. Okay, so here the conjugate base of this species is one that doesn't have any negative charge. That means it's automatically going to be more stable than each of the other ones. So off the bat, this species will be the best. We're not going to look at it in any of our comparisons between any of the negative charge bearing species. Okay, the next step is look at the resonance. Once again, there's no way for any of these negative charges to get off these atoms, so there's no resonance involved here. Once again, what we're going to be caring about is inductive effects. Here we have a lot of halides around here helping out. This is decently far away, this is decently far away, but this is even farther. So what that tells us is that since this is this is more atoms away than this, so the inductive effects here for the electron withdrawal is incredibly weak compared to these two. These two are the same distance away, so we need to look at electronegativity to be able to determine which one stabilizes more. Since fluorine is more electronegative, we could say that this has better, so I'll put a B for better, better electron withdrawing than this. And the last thing we need to look at is the orbitals involved, which are, once again, all sp3. Okay, so how do we rank them this time? Again, we're going to go from most stable to least stable. Okay, so we already decided that this one is going to be the most stable because there's no negative charge to balance, so that will be A. All right, what about B? Well, they all have the same charge-bearing atom, so once again we're going to look at the inductive effects. So this one we said had the best inductive effects because fluorine's the most electronegative and it's the closest to the charge center. Similarly, this is the same distance away, but it's slightly not as good. Next up, we have very, very slight withdrawing effects from this guy, and we have absolutely nothing from this. So this time our ranking looks like this. All right, and once again, we're going from most stable to least stable in the direction of A to E. And we are, once again, looking for decreasing pKa, just like last time. So we're going to use the same path through. We're going to go E, D, C, B, A, and you'll see that that gets you this ranking. All right, let's keep doing problems. So you should try this one on your own as well. So try this on your own. I'll give you 10 seconds. Once again, pause the video and try it out. Okay, so first thing again is convert each of these structures to line wedge structures. And those are your acids, so convert these to their conjugate bases. Once you've done that, set up your chart. Once again, you see that there's an oxygen bearing the negative charge in each of these three, and nitrogen on this last one. As far as resonance goes, we do have resonance this time. Here and here, if you push the electrons, you can see that they could go up here. Similarly for here, and there's nothing in either of these two. As far as inductive effects and orbital effects, here's what we're looking at. So again, there's nothing over here to do anything, there's nothing over here to do anything. Here we have a chlorine pulling some electron density away, and here there's nothing going on. Okay, so we already know that this one is going to be the worst because oxygen is more electronegative. This one has, well, these two have resonance, this one doesn't, so it's second to last. This one has beneficial inductive effects, so it's going to be the best, and that leaves this one here. The question asks us for weak to strong acid strength, so we're looking from least stable to most stable, so we're going DCBA, and that will look like this. Okay, hopefully you're getting the hang of this by now. We're going to do slightly more difficult problems now. Okay, so your next problem is this. I'll give you 10 seconds once again. Pause the video, try yourself. Okay, so once again, you'll notice as we had last time, we're looking at basicity. We already have the conjugate bases. If we look at this over here, it doesn't have any negative charge. So we already know that this one is going to be the best. This one has an oxygen, and these three are carbon. I'm going to skip. There's not anything going on with resonance, and there's not anything going on with inductive effects here. So the only thing else to look at is the orbitals. So that is here. All right, since this one had no negative charge, it is the best. Oxygen is more electronegative than carbon, so this is next best, and now we're comparing these, and the only difference is the hybridization of the orbitals. So you should already remember that sp is the best because it has the most s character, then sp2, then sp3. All because of that s character. We're told to rank these in regards to decreasing basicity. So that means is that you're going from the least stable to the most stable, because the most stable one is going to be the weakest base, because remember its conjugate is the strongest acid. So again, we're going from E to A. Your ranking is going to look like this. Okay, this last problem is sort of a challenge problem. If you're an organic 1, you might not know enough about some things to be able to do this too well, but it's worth giving it a shot. So we're going to be ranking these in regards to increasing pKa. So give this a shot. I'll pause the video. Okay, so the first thing you want to do is you want to convert each of these to conjugate base, and then go through your standard process of ranking them according to those 4 criteria. As far as atom goes, these are delocalized on carbon. This is on oxygen, oxygen, sulfur, and then oxygen. Okay, here, most of them don't have resonance except for this one here, which has the benzene ring and this what is called a nitro group over here. That's probably what you're not too familiar with. The induction here is a little tricky. Most of them don't have any inductive effects, but here we have this chlorine here withdrawing, and if you didn't know, nitro group on a benzene ring is a extremely good electron withdrawing group. And lastly, we need the orbital hybridization. So again, triple bond, this is going to be sp, that'll be sp2, and the rest of them will be sp3. So again, and if we're ranking them, we want to go from most stable to least stable, and this is where you get your first exception. Before you might have said, well, okay, sulfur is larger than oxygen, so this will clearly be the best one, but that's not the case. Here you have a combination of really good resonance and really good inductive effects, so this one will be the most stable, followed by this one because sulfur beats out oxygen on these two. Here, the inductive effects win out between these. And over here, you have an SP with more S character, and then you have an SP2 with less S character. Okay, and we're told to go in the order of increasing pKa, so that's I might have increasing pKa. Okay, yeah, that's going from strong acid to weak acid, because they'll lower the pKa, it'll be strong, and then as it increases, you'll have weaker. So we're going from most stable conjugate base to least stable conjugate base, and your final ranking will be this. Okay, so hopefully that clears some things up for you, since we have questions about this every year. Just to remember what this really means in terms of the relationship between conjugate bases and acids in regards to stability. Try to understand these rules. Remember, don't obey them religiously. there's a lot of exceptions in organic chemistry, so your intuition matters a lot. And you should pick up this book because it's really helpful. All right.